Okay, so we've defined matrix multiplication and seen how that works and done a few examples. We're going to do some quick review, but before we do, let me just talk a little bit about the intuition that you want to have when you think about matrix multiplication, because this is going to be an insanely key operator for us, and it's important to understand why you'd want to do it and what it really means. So I'm going to suggest that there are two ways to think about it, just like we had two ways to think of matrix vector multiplication. And these are the two. One is to say if you're doing A times B, you're doing all possible dot products. Every dot product is a row of A and a column of B. And if you have an M by N matrix A and a P by Q matrix B, we know there are M by Q different dot products like that, right? Because there are M rows in A and Q columns of B. So one way to think about it is simply all possible dot products. That's what the matrix multiplication is giving you. And the second way is to think of it as an extension of our matrix vector multiplication way of thinking about it too, which is in terms of linear combinations. So remember that if we had a matrix times a vector, we could think of it as the vector is specifying a linear combination of the columns of the matrix. It's a little hard to get your head around, but try to do so. Every column in the matrix can be seen as a domino, and what you're doing is taking a linear combination of those dominoes. And what linear combination is it, do you ask? Well, it is the elements of the vector that you're multiplying by the matrix, okay? Same thing here, except we're just doing it more than once. Instead of one column vector on the right-hand side of the operation, we now have a matrix B, which has many columns, each of which is specifying a particular linear combination of that, okay? So let's look at an example here. So going back to our Matchmaker.com thing, right? So suppose I had a matrix rather here. And this matrix has one row for every guy. We've got Biff, Joe, and Filbert, and Dave, and Weldon, and whoever knows how many we have, right? Let's say we have 652 guys. And we ask each of them 7 survey questions. So Biff says, yeah, I really like skydiving, and no, I don't at all like snoring, and yes, I really like, trimming my nails, and I get a 3 on that, and a 5 on that, and a 2 on that. And Joe gives different answers, 9, 9, 2, 2, 4, 4, da-da-da-da-da. We've done this example a lot, right? So this is a 652 by 7 matrix. And we'll call it B for boys. All right, now we also have a girls matrix. Let's say there aren't quite as many girls in our system. There's only 548 or something, right? So this is the matrix G. And we're going to say the matrix G is 548 by 7, because each of the girls also answered 7 questions. So this is Jezebel's answers, and this is Cindy's answers, and this is Betty Lou's answers, etc., etc. There's 548 of them, right? And Jezebel says 9, 9, 2, 2, 6, 4, 3, and da-da-da-da-da, right? Okay, now, we know that in terms of matchmaker-ness, what we want to do is take the dot product of every girl with every guy, right? And that's tailor-made for this operation here, right? We want to take Biff, and we want to take his dot product with Jezebel to see if they're compatible. We also want to take Biff and take his dot product with Cindy to see if they're compatible. We also want to take Dave's vector and take it with Cindy to see if they're compatible, right? So we want to take every possible row here and every possible row here and dot product them and get a matrix of results. Now, all we have to do is combine a transpose with our matrix multiplications to do that. All we have to do is say B times G transpose, right? Because if I take G transpose, that's going to turn it on its head and give us this vector here, or matrix rather. This is G transpose. It's going to be 7 by 548, and we're going to have Jezebel in this column, and we're going to have Cindy in this column, and we're going to have Betty Lou in this column, etc., right? So if we take B times that, then that's exactly what we're getting. We're taking Biff's answers, and we're taking the dot product of that with Jezebel's answers, right? That's what the transpose did for us, is it put all the girls in columns, and that makes it possible to do every guy with every girl. And when we do that, we're going to get out a matrix, and that matrix is going to be 652 by 548. And every column, or excuse me, every row corresponds to a guy. And every column corresponds to a gal. And it's going to say Biff and Jezebel, oh boy, they're hot stuff. They're at 0.9 compatibility. Biff and Cindy, not so much. Biff and Betty Lou, they're middling. Joe and Betty Lou, though, are pretty high. Filbert, really isn't very high with anybody, it turns out, until we get down here to somebody who's his dream gal, and they're 0.99, and they end up being on a date or whatever, right? And so we have a success case from Matchmaker.com, okay? But that's a case where clearly the thing we wanted was a bunch of dot products. In fact, we wanted all possible dot products. And so it makes perfect sense to use matrix multiplication there, because we've got a bunch of things that we want to dot product together, right? Suppose we didn't want to do it boy and girl wise. Suppose we just wanted to do everybody with everybody. So let's say we have some big matrix and it's got 1,043 rows, and this has everybody in it. It's got Biff, it's got Jezebel, it's got Dave, it's got Cindy, it's got everybody in here, and we asked them all the 7 survey questions, right? And let's call this A for all. Well, if I wanted to figure out how compatible everybody is with everybody, I would just take A times A transpose. A transpose takes this matrix, flips it on its head, so now all of the survey questions run up and down, and now I'm going to take Biff's survey times his own survey, and Biff's survey times Jezebel's survey, and Biff's survey times Dave's survey, and I get this whole thing, and now I'm going to get 1,043 by 1,043 matrix, so it's square. If you think about it, it's going to be ones all along the diagonal, right? Because everybody is perfectly compatible with themselves because they answered the same survey questions as they answered. So Biff, obviously we don't want to put Biff with Biff, so we're going to have to somehow in our code say ignore the diagonal. But just in terms of compatibility, the diagonal is going to be all ones, right? And then we're going to say 0.9 and 0.3 and 0.2, and this whole thing's going to be filled up. And again, it's exactly what we want because we wanted to take a bunch of dot products, and the matrix multiplication gives us that. So that's way number 1 of thinking about it. Now, way number 2 is the linear combination way. So let's do an extension of our recipes example. Remember, we had a matrix, I keep saying that, sorry. Here, where the columns were recipes, we said here is, chocolate chippers, and here we had sugar cookies, and here we had fudge, and here we had cake, and maybe we have a zillion different recipes, but there's one column for each recipe here. And then over here is the ingredients required for that recipe. Flour, butter, eggs, chocolate chips. This thing would, of course, be bigger, but let's just make it normal size since I can't think of that many. And we're going to say that chocolate chips requires 1 cup of flour and 1 stick of butter and 2 eggs and 2 packs of chocolate chips. And sugar cookies requires 2 cups of flour and 2 cups of butter and 2 eggs and no chocolate chips. And fudge doesn't require any flour, but it requires, a ton of butter, and maybe 1 egg and maybe a ton of chocolate chips. And cake requires a lot of flour and quite a bit of butter and quite a few eggs and no chocolate chips, right? Now, we saw before that we could multiply this by a vector where the vector said, hey, how many of each recipe do I want to make? So we'd say, hey, how many chocolate chippers do you want to make for your party or whatever? How many sugar cookies? How many batches of fudge? How many cakes do you want to make? And we might say, we want just sugar cookies today, please. 2 recipes worth of that, right? So all we have to do is extend this by saying, well, what if we were doing like a camp? And this camp we were running, we needed snacks every day. And so Monday, Tuesday, Wednesday, Thursday, Friday, that's when our camp was running. And we might say Monday we were going to serve sugar cookies. Tuesday we were going to serve some chocolate chippers and some fudge, and none of those. Wednesday we're going back to the sugar cookies because we kind of like those. Thursday, we have some guests coming in, so we want to make sure we have enough for them. We're going to make some chocolate chippers, sugar cookies people are pretty tired of, but let's make some fudge, 3 batches worth, and let's bake them a cake, sure. And then Friday is the closing day of the camp, so we're going to say, let's make lots of sugar cookies, so you remember that. And then maybe we'll make some goodbye cakes, right? So what I can do if I multiply these 2 together, again, is thinking of this in terms of linear combinations. This right here says I want 0 of those vectors on Monday, because I'm not making any chocolate chip cookies on Monday. I want 2 of that vector on Monday, because I want to make 2 batches of sugar cookies there. I want none of that domino and none of that domino on Monday, right? And then I'm going to do the same thing for Tuesday. I'm going to say, well, Tuesday I want 1 of that vector and 1 of that vector. On Wednesday I want 2 of that column and none of the others, etc., etc. So when I do this multiplication, I end up getting out a thing where I get one column for each ingredient, or I'm sorry, one row for each ingredient, flour, butter, eggs, chips, whatever else I have. And then I get one column for the days of the week. And so this gives me my grand shopping list. And it says that on Monday, I need to buy 2 cups of flour, and I need to buy I didn't do that right. Sorry about that. On Monday, I need 4 cups of flour, and I need 4 sticks of butter, and I need 4 eggs, and I need no chocolate chips, right? I did that by saying, well, I want to get 2 of the second column here. So I just took this second column, and I said, well, give me 2 of that. And that gave me 4440, right? And then Tuesday, I said I want 1 of the first and 1 of the second one. So we get 1 and 11 and 3 and 12 for our Tuesday recipe. Because fudge requires so many doggone chocolate chips. That's why that number ended up big, right? And then I can keep doing that, and I get my matrix, right? So there are times when it makes sense to think of it as the all possible dot products. There's times when it makes sense of having a bunch of different linear combinations, all of the same building blocks, right? All of the same starting dominoes, all of the same columns, and we can think of it that way, right? Good stuff. Let's do a little quick review here to make sure we got these concepts. Get out your pen and pencil. And compute this. What is D times E? Matrix multiplication-wise, that's going to turn out to be 8, 4, 12, 10 if I've done my math right. Make sure you get that answer so you know how to perform that mechanical operation. What about D times I, where I is the identity matrix here? What's that going to give us? That gives us 2, negative 2, 3, 1, which is D. So you'll see the operation of the identity matrix is to give us the identical matrix back, hence its name. So the I plays the role of sort of 1 in regular multiplication, right? You basically don't get anything different than you did before. What if I pre-multiplied by I? So now I've got I times D instead of D times I. Now what do I get? And it turns out to perform the same function. So I, if you multiply before or after a matrix, you end up getting the same matrix that you had before. Notice that this is commutative. It's not by any means the case that when you multiply 2 matrices together, it doesn't matter which order you do them in. However, if one of them is the identity matrix, then that is true. Fun fact. A times B. Let's say, what do you get when you do that one? Answer is, can't perform that operation. That operation makes no sense because we have 2 columns of the A matrix, but 3 rows of the B matrix. Therefore, it cannot be done. What about B times A, though? Can we do that? And the answer is we can, and we get back a 3 by 2 that is written there. What about A times B transpose instead of A times B? What do we get if we do that? Check your math and make sure you get that answer. And if you can get that answer from this operation, that's a really good sign that you've mastered how to do matrix multiplication and transpose. Finally, what about A transpose times B instead of A times B transpose? Now what do we get? And the answer is that's another no-go, because taking A transpose does not change its dimensions, and therefore, again, we got a 2 by 2 times a 3 by 2, and since 2 is not the same as 3, we can't do it. What about A times B transpose? I'm sorry, A transpose times B transpose. Now what do we get? And again, make sure you can work out that answer and get the same thing I got there. All right, question. Let's say I've got a matrix which has these sort of funky dimensions to it. Can I perform the operation Q times Q? And if so, what is the answer I get back? What is the size? The answer is no, I cannot do that, because if Q is 4,397 by 232, then Q is the same thing, and we can't have a 232 column matrix times a 4,397 row matrix. Can't be done. What about QQ transpose? Can I do that one? Yes, and I will get back a 4397 by 4397 matrix, because taking Q transpose flips the rows into columns. I now have 4,397 columns of the Q transpose matrix. Therefore, that's what I get when I do the multiplication together. What if I do Q transpose times Q? What do I get? Now I get a 232 by 232 matrix, because I transposed the first guy, and therefore I get a completely different kind of answer than transposing the second guy. And finally, what if I transpose both of them? What do I get? Can't do it at all. Because I do Q transpose, I get a 232 by 4397 in both the left and right operands, and we've already seen that you can't do that. All right, finally, what if I take two vectors here? I'm going to say that x is a row vector, y is a column vector. What do I do if I multiply x by y and get the so-called inner product? What value is that? And the answer, it is the number 22, because it's 9 times 3 plus 1 times 1 plus negative 1 times 6, and that ends up being 22. And what if I flip those around and say, no, I'm going to say that x is actually a column vector, y is called a row vector. What do I do when I get the outer product of these, which is x times y here? And the answer is you get a completely different kind of thing. No longer do you get a scalar at all, but you get a 3 by 3 matrix. So it very much matters what order you do these operations in, because if you do q times q transpose versus q transpose times q, you get a very different kind of thing. Such is the mysterious nature of matrix multiplication.